Hello, this is Jack Jackson. We're going to look today at a continuation of our series of little videos on L'Hopital's rule. And in this video, we're going to look at limits that have the indeterminate form, either 1 to the infinity, 0 to the 0 power, or infinity to the 0 power. Now, like other indeterminate forms, these could be almost anything for the limit, and they require some extra work. And of course, they could actually be a limit of any possible real number. They could actually diverge to infinity or minus infinity. And they require a new challenge because they present a new challenge because they require us to do some other types of techniques. And the problem is, we've got this exponent up there and we like to get our hands on it. It's up there too high to reach. How do you get something that's too high to reach? Well, throw a log at it, knock it down. So what we do is we take the natural logarithm of both sides, and then when we have the logarithm of b to the u, that is u times the natural log of b. So we can use that property of logarithms right here to bring that power down. So what we do is we let y be the limit we're trying to find, take the natural logarithm of both sides, and then we use this limit, we use the property that the log of the limit is limit of the log. So kind of reverse the order of those two things, bring the logarithm inside the limit sign. Then we use this property right here to bring that power down. And then we're going to usually have the form something like 0 times infinity. So we reorder things into a single fractional form that'll either have the power, the form 0 over 0 or infinity over infinity, and then we can apply L'Hopital's rule. Now, there's one thing you got to be real careful about here, though. When you finish this, you're going to be working on this one side over and over and over and working through it, and you're eventually going to get a limit, and you think you're going to be done. But remember that this is equal to the natural log of y on the other side. So there's one additional step at the end, and that's to rewrite that to solve for y in exponential form. So if you have natural log of y equals L, then when we rewrite that solving for y, we see y is e to the power L. And so we have to remember to apply that last step at the end. It's very easy to forget to do that last step because you get so involved with the other side. And you think, oh, we finally get it down to a number, and you think, okay, we're done. But you're not. You have to do that last step. So let's see if you can apply that to this example here. Compute the limit as x goes to 0 from the right side of x to the square root of x power. Notice we took the limit from the right side because the square root of x is only defined for positives and 0. Of course, the whole thing is undefined at x equals 0 because we have 0 to the 0 power. That's one of our indeterminate forms that we're looking at in this section. So see if you can apply this, this outline of what I asked you to do up here. See if you can apply that to this function and work out the limit. After you've done your work, come back and check your answer with me here in just a few minutes. Press pause now. Alright, well here it is all worked out. Let's see. So this has the form 0 to the 0 power. So what you do in this case, or any of these three forms in this this section, is you take, you start by letting them say y equals this limit. So we're looking for y. We take the natural logarithm of both sides. Now it may look like it got nastier there, but it actually didn't, because now we can exchange the order of this limit and logarithm, provided this limit exists. Now, we use the property of logarithms that says this exponent can come out front as a coefficient, and so now we have a product of two things. Now notice this one, square root of x goes to 0, log of x goes to, well, it's log of 0, that goes to negative infinity. So that has the form 0 times negative infinity. Now I need to sort of rewrite this as a fraction and sort of move one of them to the denominator to try to get either the form 0 over 0 or infinity over infinity. I think it was easier in this case if, first of all, we think of this as x to the 1/2, and we move it to the denominator and it changes signs. That's x to the negative 1/2. So check that out. These are equivalent. And now, as x goes to 0, the top goes to negative infinity, the numerator goes to negative infinity, the denominator goes to positive infinity. And so this is the form basically infinity over infinity. So we can use L'Hopital's rule. Okay, and of course they are continuous and differentiable to the right, just to the right of 0. So that, along with that form, is enough to be able to use L'Hopital's rule, which says take the derivative of the top and bottom. Now notice every time I've recopied my ln of y equals and my limit and all that, so then I'm just focusing on the stuff that I'm changing. So again, recopy ln of y equals the limit. And now let's actually do the derivatives. And remember, this is not the quotient rule, this is the derivative of the top and the derivative of the bottom separately. So the derivative of ln of x is 1 over x. The derivative of x to the negative 1/2 is negative 1/2 x to the negative 1/2 minus 1, that's negative 3/2. Now, I'm going to multiply actually top and bottom of this fraction by negative 2x to the 3/2. Now, when I do this, the negative 1/2, the negative 2 cancels to 1. X to the negative 3/2 times x to the 3/2 is just 1. So that just cancels out the bottom altogether. So we're left with the negative 2, and here we add exponents. 3/2 plus a negative 1 is positive 1/2. And so now as x goes to 0, 0 to the 1/2 is 0, and times negative 2 is still 0, so that goes to 0. But again, be careful, we're not done yet. All the way down we have log of y equals. So log of y equals this. To solve for y, we write that as y equals e to the 0 power. E to the 0 power is 1, so y is 1. But remember, y was the limit we're looking for. So now we have established that the limit as x goes to 0 from the right of x to the square root of x is 1. And again, remember this warning, you got to do that last step at the end. It's really easy to get so involved with this right side that you forget at the end, once you get to 0, you get excited, you think you're done, you forget to raise e to that power. Of course, it's always a good thing to maybe use some technology, either maybe a table or a graph to help us kind of verify that we have the right answer, make sure it looks right. So here's a graph. Now, once again, we're looking at y equals x to the square root of x power. The square root of x is only defined for positive x's and 0, and the whole thing is undefined at 0. So what this says is that so to the left of 0, to the negative numbers, the whole thing is undefined. It's also undefined at 0. To the right of 0, at the positive numbers for x, this thing is defined. And we know that the boundary point is the point 0, 1. That's an open dot endpoint. Okay, and then let's graph it. And sure enough, 0, 1 right there is an open dot, and that's your endpoint. It looks like from there it decreases, minimums out right in here somewhere, and then increases after that. And increases actually pretty rapidly eventually. Okay, there is, just since we're doing here this, the rest of this next little part doesn't involve L'Hopital's rule, but we do have a minimum right there. Let's see if we can actually calculate the value of that minimum. And the y value of that minimum up to infinity is the range of this particular function. The domain being 0 to infinity, not including 0. So what is that? Well, to find that, we need to find the derivative of this function. So the function is x to the square root of x power, x to the power x to the 1/2. And so I can use the generalized power exponential rule. So first of all, you treat it like a power function. You take the power down front, which is x to the 1/2. Then you take the original function, but subtract 1 from the power. And then you multiply by the derivative of the base. So derivative of x is 1. Plus, you treat it as if it were an exponential function. You take the logarithm of the base, log of x, times the original function, just like it is, times the derivative of the power. The derivative of the power is 1/2 x to the negative 1/2. Okay, let's see if we can clean up a little bit here. Both of these have a base, so I can add the exponents. So it still has the x to 1/2 in the exponent. I have a negative 1 minus a half, or negative 1 plus a half is negative 1/2 there. And you got exactly the same, well, the result is the same thing here. X to the power x to the 1/2, and then we have times x to the negative 1/2. The base is the same, and you add the exponents. So you got x to the 1/2 minus 1/2 for the exponent. Those two terms, those two factors are the same right there. What's a factor of the first term, factor of the second term. And we still have the 1/2 of the log. So what I'm going to do is I'm going to factor out that common factor, and I'm also going to factor out the 1/2, so my fraction's out front. So that puts me out front a factor of 1/2 x to the power x to the 1/2 minus 1/2. Then I divide this by this, I get 2. So in other words, if I multiply 2 by this right here, I get this first term. Plus, everything else over here cancels out except for the ln of x. So if I distribute this back out, you see that I do get the same thing here. Now this is the derivative, and you want the derivative to be equal to 0. Well, the only way to, this first part can't be 0. You take x to some power, the only way you could get 0 is if the power base is 0 and the power not 0, and that doesn't happen. So that's never 0. So the only way to make it 0 is to make 2 plus natural log of x be 0, which means natural log of x is -2, which means e to the -2 equals x. So the x value right here, where this is at a minimum, is e to the -2. What's the corresponding y? Well, go back to the original function here, put e to the -2 in place of x. So I looked at it in this version. So it's e to the -2 to the power e to the -2 to the 1/2. Alright, a power to a power, we multiply powers here, and this becomes e to the -1. And then e to the -1 times the -2 is, e to the -1 is 1 over e, times -2 is -2 over e. So that's e to the power -2 over e. So the minimum actually happens at the order pair e to the -2 power, comma, e to the power -2 over e. And if you put these in a calculator, then you're going to get decimal approximations something like this, about 0.13 and about 0.48, about 0.13 here, about 0.48 here. Yeah, that looks about right. So that's our local and global minimum, and so the range there is from e to the -2 over e up to infinity. Alright, let's try another one. See if you can do this one. Actually, this is two problems here. One function, we want to compute two different limits. We have 1 minus 2x to the power 1 over x. We want to find the limit as x goes to -infinity. And then we also want to find the limit as x goes to 0. Notice it's undefined at both of those places. So let's just start by looking at this a little bit. If you let x go to -infinity, 1 over x goes to 0. So the power is 0. And -infinity times -2 is positive infinity. Add 1, that's positive infinity. So we have infinity to the 0. That's one of our forms that we want to look at this section. And then over here, what we have is, if we go to 0, 1 over 0, well, depending on which side you're coming from, either goes to infinity or -infinity. And if you put in 0 here, -2 times 0 is 0, plus 1 is 1. This is the form 1 to the infinity or 1 to the -infinity. Again, that's another one of our forms that we want to look at in this part. So do both of these in a manner similar to the last problem. So why don't you try these two, and then come back and check your answer in a few minutes. Press pause now. Okay, let's try this. The first thing I want you to notice is there's a couple little technical things here that I want to just talk about before we actually do the limits. It's actually possible for this thing to be defined when the base is negative, as long as the power is a rational number power which can be expressed as a reduced fraction with an odd number base. So, for example, if x equals 5, then 1 minus 2x to the power 1 over x is 1 minus 2 times, I didn't want 5, I wanted 3, excuse me, 3. Then we have 1 minus 2 times 3 to the power 1/3. Okay, 2 times 3 is 6, so it's 1 minus 6 is -5 for the base, and we have the 1/3 power. We have taken negative power, a negative base to a 1/3 power. It's the opposite of the base of the 5 of the absolute value of the 1/3. So in other words, this negative we can pull out front. And so this becomes 5 to the 1/3, and then take the opposite of that, or the opposite of the cube root of 5. Now that is a legitimate, irrational, negative number. So that function is defined there. But we run into lots of problems here when the base is negative. If the base is negative and the power is a rational number which is expressed as a reduced fraction with an even number denominator, that should say, and this should also say denominator. or the power is an irrational power, then the function is undefined, at least as a real number. For example, if we let x equals 2 in this expression, then we're going to get something undefined. If we plug in 2 here and 2 here, okay, then what do we get? We get a 2 here. 2 times 2 is 4. 1 minus 4 is negative 3. Negative 3 to the 1/2 or negative 3 and then square root is not a real number. We could say what it is if we are allowed to go to the complex number systems, but this one is imaginary, so it's not real. So we're only wanting real numbers here. So as far as we're concerned here, this function is undefined. So this happens like all over the place, okay? So when the base is negative, the graph is basically full of all these undefined places. It's basically just got holes everywhere. So, not everywhere, but all over the place anyway. So, as what we usually do with functions with a variable exponent, we're going to limit our attention and the domain to only x values that make the base positive, especially when it comes time to graph the function. So we're not going to even try to graph this thing or even come up with a table necessarily when the base is a negative. So that means that the base, which is 1 minus 2 to the x, will have to be positive for us. Now, when is the base positive? Okay, 1 minus 2 to the x, 2 times x is greater than 0 when 1 is greater than 2x, which is 1/2 is greater than x, or x is less than 1/2. So when x is less than 1/2 are the things that we're going to be interested in. Now, what about x equals 1/2? That's kind of an interesting thing. So we might be interested in that point too. What happens there? Actually, let's look at what happens there. Actually, that's going to be okay, because if we put in 1/2, let's see, 1/2 times 2, negative 2 is 1, and 1 minus 1 is 0. 1 over 1/2 is 2. 0 to the second power is okay, and that is actually all right there. It's actually 0. So let me see if I want this version here. So actually, we're going to be okay with 1/2 being included. Okay, but let's now turn our attention to these limits that I asked you to do. Okay, so now you should be checking your work here. We want the limit as x goes to infinity and the limit as x goes to 0. Those are two places where the whole thing is undefined. So notice in my domain, I wanted less than, let's see, this is actually greater than or equal to now. And this is less than or equal to. Okay. But we also have to throw out 0 because the power is undefined when x is 0. Okay, so we want to see what happens at x equals 0, and then also what happens as we go way out towards negative infinity, what happens out there. And then we've already seen that when we plug in 1/2, we actually get 0, so that one's okay. All right, let's look at these two limits. The steps are very similar on both of them. Let's work through the one on the left first. As we go to negative infinity, we have the form, let's see, negative 2 times negative infinity is positive infinity plus 1 is infinity. 1 over negative infinity is 0, so this is infinity to the 0. That's a form that we need to work with using this technique. So take the logarithm of both sides, switch places with the log and the limit here, bring the power out front. That's the basic technique. Then rewrite this. I rewrote it as one fraction, ln of 1 minus 2x over x. And now as x goes to minus infinity, these both go to infinity, or at least maybe infinity over negative infinity. Okay, so that's one of our forms where we can use L'Hopital's rule. So, and then these are differentiable where they're defined. So let's go ahead and take the derivative of the top and bottom, which is what L'Hopital's rule says we can do. The derivative of x is just 1. Derivative log of, say, log of u is 1 over u times the derivative of u. The derivative of 1 minus 2x is negative 2. So this rewrites as negative 2 over 1 minus 2x. We want the derivative as x goes to infinity. This one is the form basically -2 over infinity. This is going towards 0. Okay? And so that limit is 0. But remember, we're not done. That's the ln of y. Notice how that's written all the way down here? Don't forget that. If you don't write this down every step, you're likely to forget it. So here we rewrite as an exponential y equals e to the 0. Of course, e to the 0 is 1. And so we say that this limit is 1. So this says that we have a horizontal asymptote of y equals 1 on the far left. Okay, very similar steps are going on over here on the right one. In fact, the first, except for where the limit sign is going to, the first several steps are exactly the same. What we actually have in terms of a form, though, is slightly different. -2 times 0 is 0 minus, and 1 minus 0 is 1. 1 over 0 is approaching infinity, or minus infinity. So this is 1 to the infinity, or 1 to the minus infinity, depending on which side we approach 0 from. So again, that's a type of indeterminate form. And notice the steps are exactly the same as before. So I'll go through this quickly. Natural log of both sides, switch to the natural log in the limit, bring the power out front, rewrite it as log of 1 minus 2x over x. Now we check it out. As you're going to 0, the denominator is going to 0. Let's how about the top? -2 times 0 is 0, plus 1 is 1. Natural log of 1 is 0. We're going to 0 over 0. So that has the form 0 over 0. That's another form we can use. That's really the only other form. It's only two forms we can use L'Hopital's rule. 0 over 0, or plus or minus infinity over infinity. That's it. We have to get it in one of those forms if we're going to use L'Hopital's rule. But this does fit that form, so we may use L'Hopital's rule. So take the derivative of the top and the bottom separately. That's what L'Hopital's rule says to do. The derivative of x is 1, and this is, again, 1 over 1 minus 2x times -2. So again, it's really basically down to the same thing. We're able to do exactly the same steps, so it looks almost exactly like this one. Over here, though, we took the limit as x goes to minus infinity. Here we can take the limit as x goes to 0. And as x goes to 0, 2 times 0 is 0, 1 minus 0 is 1, -2 divided by 1 is -2. But that's log of y, so y is actually e to the -2. So this limit, as x goes to 0, is e to the -2 power. So this says is we have a hole in the graph at 0, comma e to the -2 power. E to the -2 is about 0.1353, so that tells you about where that hole is going to be. So here's the graph right here, and we have actually a solid endpoint right at this point at 1/2 0. So that's a solid dot endpoint. And then we have an open dot hole in the graph here at 0, comma e to the -2, I believe it was, right? Yeah. So remember, e to the -2 is about 0.135. Does that look like about 0.135? Sure it does. And then as we go out to the left, we approach the asymptote of 1. Wasn't it 1? Yes, 1. But if you look at this, there's still some gap here between this and 1. It's hard to tell if this is going to be the asymptote or not. And we've already gone out to -100. This one actually is approaching that asymptote quite slowly, so we need to zoom way out if we're going to see the asymptote a little better. So this time I zoomed out to -1000, and now you can actually see it starting to level out pretty close to the asymptote. Maybe even if we zoomed out even further, then it would become pretty much indistinguishable from the asymptote in terms of the visual appearance. Okay, let's do another practical application of this type of work. Remember that compound interest, where you compound, say, compound weekly or monthly or daily, it's an example of exponential growth. And I'm going to use these letters. I'm going to let R be the periodic interest rate. So that if you're compounding monthly, R is your monthly interest rate. If you're compounding annually, R is your annual rate. If you're compounding daily, R is your daily rate, and so forth. N is the number of periods you're going to compound this. Okay, so again, if you're compounding monthly, N is the number of months. If you're compounding weekly, N is the number of weeks. P is what we call the principal, which is the initial amount invested, and A is the amount in the count. And we have this basic exponential growth formula, which we always have. It's your initial amount times 1 plus your rate to your time, and the time here is in periods, so it's N. So there's our basic setup. But now let's add a couple other letters here. C is the number of conversions per year. So If it's compounded monthly, C is 12. If it's compounded daily, well, if you don't take into account leap year, C is 365. If it's compounded weekly, C is approximately 52. Let T be the time in years, and I be the nominal interest rate. Now, we use that word nominal because it's the interest rate in name only. So if you say, for example, it's compounded 5%, let's say 6%. Let's say it's compounded 6% interest rate compounded monthly. Then the 6% is a nominal rate. It doesn't actually earn 6% a year. It actually earns a little more than 6% a year. But the 6% would be the I, or 0.06. We'd put it in decimal form. Would be the I. And the R then, of course, would be what? Well, it's the nominal rate divided by conversions a year. So if you get 6% a year and you're going to compound monthly, what that really means is a monthly rate of 0.5% a year, 6/12. Right? And the number of conversions per year is C times T. Okay, so if there are if there are 12 conversions a year, then you take and you go for 4 years. That's 12 times 4 equals 48 times they figured out the interest. So now we substitute those things in. Let's see. Where the N is, we put C times T, and where the R is, we put I over C. And so we have this expression right here for your interest rate compounded periodically. Now, let's see what happens when we take this and we let the number of conversions approach infinity. So you could let it CB1, that's compounding every year, and you could let CB12, that would be every month, and C equals 52, that's every week, and then C equals 365, that's every day, and then you could do it every hour and every second, every minute, every second, every nanosecond, just getting closer, more and more and more bigger C's so that you're compounding more and more and more often. And the limit of this ought to be what we mean by something compounded continuously. So notice that this time, as C goes to infinity, I over C goes to 0, so we have 1 for the base, and the power goes to infinity. So this has the form 1 to the infinity. So we're going to let A, the amount, be the limit as C goes to infinity of that P here. Okay, so we're going to let A, this time A is going to be the limit of this guy. Okay, so that's the compound continuous interest. Now I'm going to pull the P out front of the limit because it's a constant, and then I'm going to divide both sides by P. And I'm going to do that before I take the logarithm. Now, take the logarithm of both sides, switch places with the log and the limit here, and then bring the power out front. That T is not changing as C changes, so I can pull it out front here. And then we have the limit here of natural log of I over C, and let's see. Don't need that many parentheses. Let me get rid of a couple of these. Okay, so that's a little cleaner there. So natural log of 1 plus I over C over 1 over C. Now what form does that thing have? As C goes to infinity, the 1 over C goes to 0. I over C goes to 0. 0 plus 1 is 1. Natural log of 1 is 0. This thing right here has the form 0 over 0. Now we can apply L'Hopital's rule. C is our variable, so we're taking our derivative with respect to C. Alright. The derivative log of u is 1 over u times the derivative of u. The derivative of I over C is I, which is a constant, times the derivative of 1 over C. And the bottom is derivative of 1 over C, so those two things cancel out. I can go ahead and figure out that derivative if I want also. That derivative would be, what, minus 1 over c squared here and here. But those two things cancel. So we've got an I in the numerator here. We got this 1 plus I over c in the denominator. This is 1, so that goes away. So we have that. Now we still have our limit. We still have our t. We still have this logarithm over here. Now what happens is c goes to infinity here. If c goes to infinity, I over c goes to 0. 0 plus 1 is 1. I divided by 1 is I. So this limit approaches I, which is times that t, so it's it. Now we rewrite in terms of, we want to solve for a, so we rewrite in terms of exponentials that a over p is e to the it, and multiply both sides by p, a equals p e to the it. Usually I write this I with the k. Some people write it with an r, but I already use r for something else, and I always use r for the periodic interest rate, so I always use a k here. So a equals p e to the kt. That is the basic formula for compound interest where it's compounded continuously. And what is that k? That k is the I, the nominal interest rate, when it is compounded continuously. And so we prove the compound continuous formula for interest, which I'm sure you've used before in your algebra classes. Okay. In fact, one way, because of this, one way you can think of E is this, and this is the way I always approach it in my algebra classes when we introduce the letter E, is you can switch from any base you want to a base to any other base, but then what happens is you pick up a constant here, like 8 to the t power is 2 to the 3t power. So it picks up a number in front of the t there when you do that. But E is the right base to use so that when you write an expression like this, that coefficient k is the same as the nominal rate of growth, nominal percentage rate of growth. In other words, k is your nominal interest rate. So if it's interest compounded continuously and it says it's 5% compounded continuously, the k would actually be the 0.05. So there's a real-world example where we use this particular type of limit to work out a formula.